All right, hi everybody, and welcome to your 2.1.2 video notes. So 2.1.2 covers this idea of modeling with parabolas. So the word modeling you hear thrown around, especially in CPM, where we're modeling with something, and modeling in math just means using math to represent a real world situation. So representing a situation with parabolas, that's what we're going to do. So yesterday in class, we finished up 2.1.1, which remember was on this general graphing form, a times x minus h squared plus k of a parabola, and where we got more and more comfortable with predicting and sketching and telling information about a parabola based on these values of a, h, and k. So we're going to build off of our understanding of that and use it to represent real world situations. So we're going to start here with number 2-13. And let me change my pointer. I just want to show you this lightsaber pointer that I have, and I found that it's actually a little distracting, although it's cute and fun. I just wanted to show you that. Okay, I'm going to stick with this one. All right, so we know these three parameters and what they do to a graph of a parabola. So here we're going to read through this. So this diagram at the right shows a jackrabbit jumping over a 3-foot high fence. To just clear the fence, the rabbit must start its jump at a point 4 feet from the fence. So we're talking about to make it over, this rabbit has to be 4 feet away from the fence, which means overall it jumps 4 feet on both sides, which is where we get this 8 feet from. So it's got to be 4 feet away. We are told to sketch the situation. So that's step 1. Step 2, write an equation that models the situation. Show or explain how you know your sketch and equation fit the situation. So we're going to walk through this together. And I'm actually going to show you this process 2 times, and I think the second version of it will make a little, I think the second version is easier, but I'll let you decide and you can use whichever works better for you. So we're going to sketch this first. So obviously we're modeling parabolas because that's what the whole section is on. You can see this top piece of a parabola that's going to be formed by the motion of this jackrabbit jumping. So in terms of where the vertex is, that's where I would consider starting. And you can kind of choose where that vertex is on our graph. It's 3 feet off of the ground. So let's say that this x-axis is the ground level. That would mean the vertex would be here at 0,3. And then since the jackrabbit had to be 4 feet away in order to clear that jump, it needed to be 4 feet away. So 4 feet on each side of the y-axis would give me the points -4, 0, and 4, 0. So then we can see this parabola that would model the situation. Let me try a little bit better. Would look something like that. So the next task is, what is the equation? And again, we have this starting value, or this starting equation where, we've got y equals a, x minus h squared plus k. And from our time with this equation yesterday, we grew more and more comfortable with taking information about a parabola and determining how that graph would look. And now we have the vertex, which we know from yesterday is h comma k, which means I can just go ahead and substitute those 2 values into my equation, and then we're just one step closer to determining the final equation. So we've got y equals a times x minus h, which would be x minus 0 squared, which is just x. So you could write x minus 0 squared, but it's just kind of unnecessary since x minus 0 is 0, or x. So I'm going to write a times x squared plus k, which is 3. All right, so I am already, just from the vertex alone, super close to having this entire equation. I just don't know this value of a. So that's my only problem, is how am I going to get this value of a, which again tells us the stretch factor, or is it compressed or stretched, and also if it's opening up or down. This is opening down, so right away we know a, when we solve for it, should be negative. The way we're going to solve for it is using one of these 2 points that we already put on our parabola, because if we know both of these are on our parabola, then we should be able to plug one of those coordinates in for x and y, and then we can solve for a. So I'm going to choose to plug in this point right here. So the point 4, 0 is on my parabola. So I can plug that in, and the x value is, the y value is 0, a times x, which is 4 squared plus 3. So now my only unknown in this equation is a, so I can just continue solving for that to get a by itself. So we've got 0 equals 4 squared is 16, so 16 times a plus 3. We can subtract 3 from both sides, and we end up with -3 equals 16a, and then finally divide by 16. And we have a equals -3 over 16. And you can just leave it like that. So in the end, we have, this is what we started with when we plugged in our vertex of 0, 3. And then we just needed to figure out what that a was. We pick a value, or we pick a ordered pair on our actual parabola to replace x and y with, and then we get a by itself. So now we have our final equation, which is y equals a, which is -3/16 times x squared plus 3. So this is that equation for this exact parabola. So if you have a graphing calculator or at your computer, I would encourage you to plug this equation in really quick. Just plug it into your graphing calculator, into your y equals, or into Desmos, and you should expect to see this exact graph, which is pretty satisfying when we just figured out what that equation was by hand. Okay, so I'm going to repeat the steps of this problem, but I'm going to do it in a different way, and I like doing it this second way. I just think it's a little bit easier when you're plugging in points. So the second way would be if instead of forming my graph like this, if I actually only used this quadrant 1, meaning this positive x and y space. I don't think I can erase any of this. No, I can't. Okay, that's all right. I'm going to just work on top of what I did. So let's say that instead of forming my graph like this, where I had the vertex at 0, 3, what if I made the start of the jump over here, where the rabbit starts, if I made that the origin? So let's say he was starting to jump right here. And that means the point 0, 0 is on my graph, and I'm doing that intentionally. Now he had to jump 4 feet over, and then he was 3 feet high. So that would put the vertex at 4, 3 instead of 0, 3. And then 4 more feet over, he would hit the ground again. So it's just taking this parabola and representing it so that the origin is part of it. Okay, so in the process of doing that, we've changed the vertex. So it's no longer 0, 3, it's actually 4, 3. So when I go to write my equation, instead of this one right here where I plugged in 0, 3, now I'm going to plug in 4, 3. So let's see, if my vertex is 4, 3 instead, then my equation would be y equals a times x minus, remember this is my h, that's my k, so that would be x minus 4 squared plus 3. So I've plugged in my h and k values, which is different than this because I chose a different vertex, remember. And then at this point is where I choose a point remember, I just need to figure out what A is. So all I need to do now is choose a point on the parabola to plug in for x and y, and I intentionally made this graph so that 0, 0 was on my parabola, so that when I go to plug in 0, 0 for x and y, things simplify pretty easily. So we've got 0 in for y equals a times 0 in for x, which is just 0 minus 4, or negative 4 squared plus 3. And then we've got 0 equals negative 4 squared is positive 16, a plus 3. We subtract 3 from both sides, so this is going to start looking familiar. And as I continue solving for a, I end up getting the same value for a, and that should make sense because it's the exact same parabola. It's just been shifted over 4 to form this one. So the final answer for this one, this green parabola, would be, I have my value of a, it's negative 3 over 16, x minus 4 squared plus 3. So this is a correct answer, as well as the first one we did. These are both correct. So there's more than one correct answer you could use to model this situation. It just depends on where you make that vertex. Do I put it right here on the y-axis, or do I just do the whole thing in quadrant 1 so that 0, 0 is always a point on my graph? I like using 0, 0 as a point on my graph just because it's easier to plug in the point 0, 0. But like I said, if you liked our first version of doing this better, then you can stick with that. There's more than one correct way to do these problems. Okay, so now that you've seen one full example and in 2 different ways, let's do another one to just get that practice and just solidify our understanding of this. Okay, so we've got another one. So Miss BB kicked a soccer ball. It traveled a horizontal distance of 150 feet total. So a total horizontal distance of 150 feet. So that means it went that way, 150 feet. And it reached a height of 100 feet at its highest point. So sketch the path of the ball and write the equation for the parabola that models the ball. So I'm going to go with my preferred method, which is using the point 0, 0 on the graph. So remember that someone kicked a ball and it traveled a total of 150 feet. So I'm going to make the origin kind of the starting point of where that ball started to where it was kicked, and it traveled a total of 150 feet. So 150 would be over here. So the path of this ball, let's see, it said it reached a height of 100. So we'll put 100 here, and we know the vertex is going to be right there at in between 0 and 150, which is 75 feet, and then we were told it was at its highest point of 100. So that makes the vertex 75, 100. All right, so I'm going to write that over here as well. 75, 100. Again, that 75 is coming from the fact that it went a total of 150 feet. And the laws of physics actually, if you ever take a physics class that's more focused on objects in motion, you will learn that, it's the same idea of what goes up must come down, and it actually comes down in the same amount of time it took to go up, which is kind of cool. So what goes up right here, halfway in between the total horizontal distance, is 75. Okay, so the path of this ball looked like this. Someone kicked it, it went up. Oh, that's not a good path of a ball. Okay, then it came down. All right, so this is forming a parabola that we want to figure out what the equation was. All right, so going from my original equation of y equals a times x minus h squared plus k. I would write that equation out every time. The more times you write it down, the more that is committed to memory. So h and k So my h is 75, k is 100. So now I can write that in. Y equals a times x minus 75 squared plus 100. And now I'm almost done writing the equation for my parabola. I just need to know the value of a, or what is that stretch factor or compression or whatever it is that's making it get that exact shape. This is opening downward, so I should expect that to be negative. And I can choose a point on this parabola. Remember, I intentionally made mine start at the origin so that I can just plug in the point 0, 0 for x and y. So y is 0, a 0 minus 75 squared, that's just negative 75 squared plus 100. So now I need to subtract 100 from both sides in my quest to solve for a. That is meant to be a multiplication symbol. So let's figure out what negative 75 squared is. That's 5625. All right, subtract 100. And negative 75 squared is 5,625 times a. So to solve for a, all I need to do is divide both sides by 5,625. I get negative 100 over 5,625. And that ends up being a decimal. I would actually just leave it like this, but simplify the fraction. You could just leave this value for a. That would be totally fine too. But I'm going to reduce it because, you know, I'm a math teacher. So looking at this fraction, I see 100 and my denominator ends in 25. And we all know 25 can go into 100 an even number of times. So I'm going to reduce this by dividing 25 out of both the numerator and denominator and getting an a value of negative 4 over 5625 divided by 25, which is 225. Okay. So I have my value of a to substitute into this equation. That is our final equation. So I'm going to write that in my answer blank. That is far too small for what I need. So that is y equals negative 4 over 225 times x minus 75 squared plus 100. So this is my final equation modeling the path of that soccer ball. Again, if you have a graphing calculator or your Desmos calculator open, it's pretty cool to graph that and see it match perfectly to the situation we sketched right here. So it should look just like what we wanted it to, with the vertex at 75, 100. It spans out to an x horizontal distance of 150. Okay, so this part B question is asking how far was the ball from Miss BB. So she's standing right here. She kicked the ball right here. Kick the ball. There we go. That's a person kicking a ball, I guess. Okay. And how far was it when the ball was 25 feet high? So to solve that, let's see. Let's just look at the graph. And that ball was 25 feet high twice. Again, it's that idea of what goes up must come down. So if 25, that's 100 right here. 50 and then 25 would be maybe 25 feet high there. And then when it comes down, it hits that height too. It was asking how far away was the ball. So there's going to be two answers for this, and we can figure that out now that we have the equation. So we have this equation that we can use to figure out how far horizontally, which is what is x when the ball is 25 feet high. In other words, when y equals 25. So this would mean setting up our equation by plugging in a y value of 25. So that would be 25 equals negative 4 over 225 x minus 75 squared plus 100. So at this point, you would solve for x. So that's going to take several steps involved here, but I'm not going to go through these steps here. My focus is that you guys can take oh, why did that happen? That you guys can take a, there, real life equation and begin to build the equation for the parabola by determining first the vertex, HK, and then plugging in a point to determine the value of A. Okay, so one last example. Oops, all right, let me zoom in. All right, so I like this problem, but I'm not going to walk through it with you because I want to see if you can do this independently now. So it's very similar. It's got another situation. You will sketch the situation, determine the vertex, and use that to finish writing the equation. So I will walk through this sketch with you, and then my goal is that you would pause and work through this on your own. So at the skate park, the hot new attraction is the U-dip, a cement structure embedded into the ground, aka a half pipe if you skateboard or snowboard. So the cross-sectional view is a parabola that dips 15 feet below the ground. So that's helpful to us because we know the vertex is going to be at -15. And the width at its widest part is 40 feet across, meaning from the opening to the other side is 40. And then it dips down to -15. So here's the sketch of it. And then you've got this vertex at, if it's a total of 40 feet across, then right in the middle is 20. 20, -15. So I would like you guys to pause the video. I'm going to end up writing the equation, but I'm not going to show the work for it. So my goal is that you can walk through the steps to determine the equation by substituting our H and K into the equation and then solving for A. So go ahead and pause the video, see if you can walk through that equation, and in the end, you should end up with this. Okay. All right. So there's the answer, but you guys need to show me the work for that. All right. That is it for today. Thanks so much, guys. Hope you have a great rest.